I tasked her with building a crossbar memory and to also make us some transparent memory, because if this is made out of silicon oxide, you can just use glass and it could potentially be a transparent memory. Now, the memory you have in your phone is not transparent, but if it could be, that would be really neat. So that glass panel on the front, instead of just being a piece of glass with indium tin oxide on it, it could be your memory as well. So I had one woman say, you cannot build a crossbar out of this. She went to the lab, she tried, and she said it's impossible. But she was convinced it could not be done. And I hired Javan Lin, and I didn't tell him what she said, and he made it work. And this is what happens. I mean, you just don't tell them that it can't be done, and somehow they get it to work. Today we're going to learn about carbon to silicon oxide nanoelectronics. And what you're going to see today is how research evolves from the laboratory to the industry. I'm going to take you through the whole sequence and how we didn't mean to work on silicon oxide electronics. It just evolved that way. And so this is kind of a story of the people and how this story came about. So this work was actually featured on the front page, top half of the New York Times in August 31st, 2010. Advances offer path to shrink computer chip. You can see this path here, and then it continued over on page A12, and it talks about what was developed. So here's the key person right here, Jun Yao. Jun Yao is the key person, and Jun Yao had the distinction of working for 3 different professors toward his PhD. So he was in my lab, but he also worked for Doug Nadelson in physics, and he also worked for Lin Zhang, who was in computer science. And so he had 3 bosses he had to please. Zhenzong's son is a professor now. He assisted him a little bit. Zhenzong's son is a professor at Fudan University. It's a very good school in China. And Jun Yao is a professor at University of Massachusetts at Amherst right now. But here's the key players and how it evolved. So the first person to work in this area was Professor Yubo Li. I could not find a picture of Yubo. I went to his university. He's at Hebei University in China now as a professor, and their website was down last year when I tried to pull this together, and it's down this year when I tried to pull it together. You go to the faculty page, there's nothing. So they need to fix their website. So I just couldn't get a picture of Yubo Li. But then Alexander Sinitsky took over. Alexander was a visiting graduate student. Yubo was a postdoc, and then Alexander was at Moscow State University and then worked with him. Then when Alexander finished his degree at Moscow State, he came to work for me as a postdoc. He's now a professor at University of Nebraska. Jun Yao is, like I said, at University of Massachusetts at Amherst. And then after Jun Yao, Javan Lin took over. He's at the University of Missouri. So all of the people who worked on this have become professors. And there's one other person that I couldn't fit on that slide. That's Ganuk Wang, who is now a professor at the Graduate School of Converging Science and Technology at Korea University. So the 5 people that really took the lead on this have all become professors now. If you do not believe in the physical resurrection of Jesus Christ, send me an email, tour@drjamestour.org, and we will get together, and I will share with you about why I embrace the resurrection of Jesus. And so right now, non-volatile memory, NVM, non-volatile memory, is a big market. And non-volatile memory means memory where you can turn off your computer and it holds its memory state. So if you're just typing on your computer, that's not stored. That's not stored in flash memory. That's not backed up in that way. So if your computer dies, it's lost, unless you have this constant backup, which is constantly reflecting it to the cloud. But even that takes a few seconds before but so you're not going to lose much. But if you turn off your computer and you lose that, that's a volatile memory. Non-volatile memory, right now, there's many ways to do it. It used to be based on a magnetic spin states, that a magnet would flip over these things and you had a spinning hard drive, and when you'd hit save, you could hear the drive go bzzz, spinning around and saving. Now it's all saved in flash. And what flash is, it's a normal transistor. It has a source, a drain, and a gate. So in that way, it's a normal transistor. But there's this floating gate, this deep trench capacitor, where it can store these charges. So it took a normal transistor, what was a normal transistor, and put this floating gate on it. And this is what your flash memory is. This is how the memory is stored in your phone and your computer and all your devices and all your little things. It's all in flash memory. So it's a very, very big market, non-volatile memory. This is why you can turn off your phone and turn your phone back on, and it hasn't lost anything, because it has all been stored in non-volatile memory. Non-volatile, again, meaning that you can turn the power off and it stores it. So here it stores the electrons. The problem is this is becoming smaller and smaller. This floating gate gets really small, and so you just get down to where you just have a handful of electrons as your stored information. So as that gets smaller and smaller, you're only holding a few electrons, and then if one electron leaks out, you know your memory state can go. Now there are ways of stacking up. So in other words, it was thought that memory is just 0 or 1. It's got a bit of information or it doesn't. That's no longer the case. Memory will can have multiple states. In other words, like 10 states. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different states. So in other words, you may have heard of Moore's law, which puts more devices on a chip every 18 to 24 months. It doubles the number of devices on a chip. And Moore's law has been holding since the early 1960s. It's not that they've really been putting more devices on there. They've been getting higher functionality too. So in other words, if you double the amount, if you go from 2 states to 4 states, you have double the amount of information that transistor can hold. So you didn't have to put in another transistor. You just put higher functionality into that transistor. That's one of the games they play to keep up with Moore's law. It's really amazing how they've done that. But as everything gets smaller and smaller, you get fewer and fewer electrons, so that a little bit of electron leakage going out and your memory state could be lost. So that's part of the problem. So they've thought of a lot of different types of memories. And the type of memory that we're going to talk about today is to call RRAM. So it's a resistive random access memory. Resistive. Some people call it ReRAM, R-E-R-A-M. Some people just call it RRAM, is resistive random access memory. And so here's how it evolved in our laboratory. Yubo Lee had what was called nano cables. He had worked on this sort of thing as a graduate student, and now when he came, he knew how to make these. And these were silicon oxide covered in a graphitic layer. It looks like graphene. It's not really graphene. It's really broken and distorted. So it's more of an amorphous carbon layer. I put G because you can see little sheets. What amorphous carbon is, just tiny little sheets of graphene here, but amorphous carbon layers. So you have about 10 layers of amorphous carbon here, and then the rest is silicon oxide. And so he put it down on the surface, and then he evaporated 2 platinum leads on it in the clean room here. And so this is what these nanocable compositions were. It was these layers of carbon, and then you had some silicon oxide, and then some silicon in the middle. Silicon oxide, you're always going to have a native silicon, you're going to have some silicon oxide coating. And so that's what these nanocables were. And he was able to get some switching states. So if you start driving a voltage across this thing, the current, so this is the voltage current curve, the current goes up as the voltage goes up, and then all of a sudden at some point, boom, it goes down. And that was, at some point, this wire would just break. And so you could have an on state and an off state, but it was interesting. So if you ramp it up, it goes, at some point, boom, it goes down. And then if you go back to 0 and try to ramp it again, you're in a zero state. It's left over from this state, stays in a zero state, and then at some point, boom, it goes back up and then follows the original curve that you were on, again, breaking. And then if you do it again, it follows this zero state that it was in, follows it, and then it starts ramping up again to do this. But then what happens is if you scan it back, it will go back to its original state. So you actually had two states. You had this off state, and you had this on state. This on state where it starts ramping up immediately from zero, or it doesn't ramp up from zero. So those are the two states, off and on. And the difference between off and on was very large. So here you are at like 10 to the minus, if you're reading here at 1 volt, you're 10 to the minus 11 amps, and here you're 10 to the minus 5 amps. So you have 10 to the 6th on to off ratio. That's very good. Just to put it in perspective for you, if you had a 10 to 1 on to off ratio and you had a crossbar memory where they're all lined up, 10 offs will look like an on, because 10 offs have the same current as 1/10 of an on. So 10 offs in a row would look like an on. So you can't build a very big memory, because if it's just 10 by 10, 10 offs can look like an on state. But if you have 6 or 7 orders of magnitude, now you can have a much bigger memory array without having to worry about that. And so you could it's either an off state or an on state. You write it out here and you erase it by going up to a higher voltage, boom, and the thing erases. So this is what he noticed, and this was a little memory. And so he showed that you could have it in the off state, read it several times, it's off, give the high voltage pulse, and turn it back into the on state by scanning it back. You can have it back in the on state. So you can have on state, you can read it several times, off state. And you see you're going, in this case, from 10 to the minus 12 to 10 to the minus 5. So you're going 7 orders of magnitude in difference in current. And so you could tell when it was off, you could tell when it was on. And you can see you can read it many times in its on state, and then you erase it, boom. It goes into its off state of being around 10 to the minus 12, sometimes 10 to the minus 13, but this is the off state. You can read it many times, and then you write to it, boom. And so this is a memory. You can write to it and erase it, and it's very clean, and it's going at room temperature. This is what he noticed. And so Alexander Sinitsky, who was helping him, drew this picture, and it turns out that when it would go up to the high voltage and then break like this, actually this carbon sheet on the outside of it was actually physically breaking. So in other words, here's one of these nano cables, and it's sitting between 2 platinum leads, and you can see after the switching event, it gets a crack across the surface. And the crack is generally right in the middle, far away from the electrodes. For the same reason, if you have the old incandescent light bulbs, and remember how the wire would break and your light bulb would no longer work? Remember before LEDs? Do you remember when there were no LEDs and you had these incandescent bulbs? Anyway, if you looked at that wire in the middle, the wire was always broken near the middle because at the electrodes, it's cooling. It gets cooling from the sides. There's a sink. So the hottest place is going to be right in the middle. And so it would break. And so our thought was that you had a little bit of carbon opening and then closing, that this was the read and write mechanism. That's totally wrong, but that was our mechanism. And we wrote the paper and we were going to publish it like this. And in fact, the first draft of the paper that we submitted showed this sort of model. And then we learned that we could do it. You didn't just have to have the cable. You could make a patterned stripes on a surface. So in other words, we could evaporate carbon on a surface, and then we could put some leads down here, and then we could etch away, put some chromium on the surface. Then we could etch away all the existing carbon, just leaving it under that chromium, and then remove the chromium, and you just have these wires, and then we can put platinum leads across it. And you could get the same sort of thing. You could get a switching state where you had these two states, where you could go on and you could run it forward and back, But then if you run it down, and then you go from here over to here, it stays down. But once you go back, if you scan back, it will have this state. So the two states are, this is off, this is on. So this was the off state, this is the on state. And you could see with these stripes, again, you would see the breaking in it. So the thing would physically break. And that was the memory. But all of this on the surface is horizontal. It's all horizontal. But to have any good packing in a computer, things have to be vertical so you can pack them in. So instead of having big structures like this, taking up a lot of your 2D space, you turn them so that now they're thin and you can pack a lot more together. That's how computer chips are made. They have many levels in the third dimension. And so we wanted to do this inside a cavity like this. So we wanted to have it inside the cavity where we could put carbon in there and have it vertical. And so we built this, and we built these vertical carbon rods, and then we would do this. But the question comes, when you're filling this with carbon, will it really fill like this? Would it really fill like this to fill the thing up? Or would it fill the cavity and leave an opening? So in other words, these are very small dimensions we're working on. So this hole here is, something smaller than 100 nanometers. So the hole may be 50 nanometers, which compared to current day electronics is big. But this is what we were doing with our clean room at the time in probably 2005 or something like that at the time. And so we were filling these holes, 2006, somewhere in there, and filling this. And it turns out it didn't fill all the way. And so when we would cut it open to look at it, you had carbon on the sides, but it wasn't filling it up into a rod, but it didn't matter. Because we could have the off state, we could have the on state, same sort of thing. Here we are 10 to the minus 11 to 10 to the minus 5, and we would get cracks. We'd get this little crack at the edge, and you could have the on state, you could have the off state, so you could have your memory. All of the memory, every time you've saved anything on your phone, on your computer, it's all going into non-volatile memory. Now, it's not working on this, it's not working on our RAM, it's working on that flash memory that I showed you, that storage of electrons in that capacitor there. But memory is a very, very big market. And for people who think that, probably the real drivers of this are scientists with their, big databases and everything. It's not. It's all media. It's all entertainment. Entertainment is the biggest driver of memory, for sure. Just a quick reminder, this organization is run totally by volunteers, but we do have to pay for the production work. If you could help us out by going to give.jesusandscience.org, we'd appreciate it, or you can click in the description box below. If you can't give, we certainly understand, but please just give us a thumbs up and click subscribe. Thank you. So then, instead of doing vertical holes, we thought we'd do holes like this at an angle so that it's much easier to fill with carbon. So you'd fill this thing with carbon, then you'd put on a top lead, and then you'd use UV ozone to trim off the edges. And so the way this is done, you have silicon oxide, you have these tools in the clean room here that can drill out holes like this. And in fact, holes without vertical walls are easier to make than holes with angled walls. And that's because when you use an electron beam to dig out a hole, what happens is it comes in very vertically, but then some of it backscatters. And so when it comes out like this, because some of it is backscattering, and it opens up these holes like this. And you evaporate carbon into this by sputtering, and then you put on this tungsten electrode, and then you just use UV ozone. Ozone clips off carbon, turns it into CO2, and so now you get your carbon filament. And then what we're going to do is we're going to put a voltage high enough across this to break this. And so you get your switching states. So this is now in the vertical. So we took it horizontal, moved it to the vertical. And the reason I knew to do this is that I was visiting IBM Thomas J. Watson Research Center in upstate New York, and I was showing him these planar arrays of these carbon sheets where we could make these into memory. He says, yeah, you'll never be able to get that packed in. You're going to have it vertical. And so this was the try to go ahead and make this vertical. So you have this on state and off state. And the other thing about this is it was radiation hard. That was really amazing. So in other words, and it was temperature hard. We could heat this to 200 degrees centigrade and we never lost the memory state. It turns out we can heat this to 600 degrees centigrade. It doesn't lose the memory. That's a very big deal because chips can get very hot and you can lose memory states. But also we expose this to X-ray radiation, 20 megarads of X-ray radiation. Flash memory fails at 5 to 15 kilorads. This is 20 megarads of radiation. And so you can see here's the on state, here's the off state. On state, off state. And so this is at 200 degrees, and then you can also expose it to X-rays, and actually the off state actually even gets a little more off. It gets even better. So this is, and so it's hardened. And then we expose it to a proton beam up at Texas A&M. You expose it to a proton beam, and here's the on state before exposure, the on state after exposure. These are almost the same. And the off state before exposure actually got better after exposure, got more off. So this is radiation hard. And you said, I don't care about radiation hard. I don't plan on walking in front of a proton beam or anything. Well, what happens if there is some nuclear blast? And, everybody's going to be upset and stuff, but all the memory on your cell phone is gone. Talk about misery. All of this is going to be gone. And so to have hardened electronics is particularly important in the military, to have radiation hard electronics. And so radiation hardening to heavy ion. And so this one was tested at Sandia Lab and at Texas A&M. And so here's the on state before radiation. Here's the on state after radiation. So just a very slight amount of loss. And then the off state before and after radiation is right about the same. So this was a radiation hard memory. So again, this is just an academic exercise. We're going through and we're learning this. We said, wow, this is a really great memory. And so you can see the evolution of this. It went from these nano cables flat on a surface. Then we had looked at some vertical designs. I didn't show you this because we're just cutting out just in lieu of time here. And then we went to other planar surfaces with these carbon lines. And then we went to this vertical configuration so that you could pack them together. And here was our model. Our model was that when we get this breaking, remember that we were forming some carbon filament is in the off state. It's open. It's an open circuit. And then the circuit closes. And then you have this written to state. And so the idea was that we had some sort of layer here would break. Now there was this guy Stanley in the literature just about the same time. So we had published this in Nature Materials 2008. The same year, Stanley comes out and he says, if you just take these sheets of graphene, you're forming some carbon filament between them. It's on a silicon oxide surface, you're forming a carbon. So he was suggesting exactly the same mechanism that we were suggesting. Now, mechanisms are often conjecture. You have a conjecture on a mechanism. That's just the way it is, and sometimes the mechanism is right, sometimes it's wrong. But the effect is there. How you interpret the effect going is important to help you to understand and make it better, but the effect works. And then in 2009, we published based on these carbon lines. So in 2008, we had these nano cables, and then we had these carbon lines. So this was Yubo Lee, had published this. Alexander Sinitsky was the first author on this with these carbon lines. Same sort of thing. At the time that we published this, I put in one sentence during the revision stage before it was published. And I said, this might be because of the underlying silicon. And Alexander did not want me to put that statement in there. And I put it in there anyway because I said, because if it's wrong, it's not going to really matter. But if it's right, it helps us to substantiate our paper a lot more. And I'll tell you why in a moment, why I put that in there. And it's because of this, because of Jun Yao, this wonderful student who worked for 3 people here at Rice and had to keep 3 professors happy and not just one, and is now a professor at UMass Amherst. His idea was this, that you're getting a breakdown of the silicon oxide, the underlying layer. That when you have these 2 carbons where it's broken right between them, you damage the silicon layer underneath because of the very high temperatures that were here, and you're getting a filament of silicon buried within the silicon oxide. And that's your switch. It's the opening and the closing of the silicon. And I remember we sat in a group meeting in my office, Alexander Sinitsky was presenting, and Jun Yao said, I don't think that's the mechanism. I think it has to do with this underlying silicon oxide. And people were like, what are you talking about? And it was a Russian guy, Alexander Sinitsky, from Moscow State University, who's convinced that it was this carbon switching. And there now you had a Chinese student suggesting that it was silicon oxide. And generally, the Russians are much more aggressive than the Chinese. Chinese are, they stand up. When I stand up in my office, they stand up. They don't sit down until I sit down. I mean, very respectful. And the Russians, just come in and, hey, comrade, or whatever. They're just, and he just wanted to quiet this Chinese student. Like, what are you talking about? And I said, no, let's just hear him out. He said, look, silicon oxide is a dielectric. It's not a switch. At the time, we had funding from SanDisk. You ever heard of SanDisk? You might have had little memory sticks, are often made by SanDisk. And they had we were funded by them to develop this carbon switching. Well, Jun Yao started to show, I said, Jun, go ahead. If you think this, go ahead and show it. And because of Jun Yao saying that at the group meeting, I put that in the paper. I put like one sentence, this could be from silicon oxide breakdown, getting silicon filaments. And Alexander didn't want me to do that, and it turned out that was right. So he started to test this. He took a carbon filament with these 2 platinum leads on silicon oxide, and boom, he got the switching to occur. And he got the same sort of switching, and you see this breaking in the carbon. But now what he did is he put a carbon nanotube there. He brought up the voltage till it broke, and you see this damage to the underlying silicon around it. It's sitting on a silicon wafer, and you can see the silicon is damaged from the high heat that occurred. So that gets very hot before it breaks. And if you look closer, you can see all this damage to the underlying silicon. So he was suspecting it's this underlying silicon. And then he switched to a single wall carbon nanotube. So here you needed AFM to see it. Because it's such a small tube. And again, he's got the same type of switching, just in a single wall carbon nanotube. But again, Alexander Sinitsky pounding the table saying, well, it's still carbon. It's carbon switching. You get it? It's carbon switching. You have a multi-wall carbon nanotube, you have a single wall carbon nanotube, it's carbon. So then he went without carbon. He just put titanium nitride as the layer, no carbon. And he got the same switching. Because it's just damaging the silicon oxide underneath. It doesn't matter what damaged it, it's all silicon oxide switching. It's all silicon filament forming. And then Alexander says, no, there's so much carbon floating around in the air, our labs are full of carbon, and this is looking like, maybe Jun is right. And so then he went to metal islands. He didn't do titanium nitride, he just put metal islands between 2 platinum leads. And he got the same sort of switching because it's just damaging this. The only common element here is silicon oxide underneath. And then he went to tungsten wires and silicon oxide. So just tungsten, just the 2 electrodes, and he put a high enough voltage across them that it damaged the silicon between them, and boom, he got the same sort of switching. So at this point, Alexander's, rethinking this thing, that this Chinese kid's pretty smart, and he's figuring this thing out. And I really have to credit him because so many people were against him. I had not just Alexander, I had like 3 Russians in my group. I love Russians. I mean, they're trained super well, and they're very smart. And they all were ganging up on, poor little Jun Yao. And they were all taking the side of Alexander Sinitsky. So this is part of the dynamic that goes on in a laboratory. And this is what you see, but this is the evolution of what happened. And so then he went to metal, silicon oxide, silicon. So it only had silicon on one side and metal on the other, and he did the same sort of thing. And he did it in vertical arrays with PECVD silicon, all sorts of different silicon oxide. And he could build in multiple memory states. So you see there's 1 state, 2, 3 states here. So the multiple memory states. So you see there's 1 state, there's another states, and there's another switching state. So you're building in multifunctionality into these RRAMs. And so then he went to a different scenario where he has this vertical array and he has polysilicon on one side, polysilicon on the other side. And by this time, Alexander's already graduated and already gone to get his job. And so Jun Yao is working as a graduate student, and he's showing that you just get damage to the edge of this silicon and you get the same switching states occurring. And so you can see after switching, you get this damaged edge. So here's how the edge started out, and here's how the edge ended up. And you get in here, some silicon oxide filament is forming in this thing. You get damage right on the edge. It's just a little nub here. It's from this little nub he's building these switching states. So once he understood that it was silicon oxide, he could make all sorts of different arrangements. So here's all the different pieces. So it didn't matter what the electrode was made out of, and it was intrinsic to the silicon oxide. The device size didn't matter. The current, it didn't matter what the diameter of the device was. The current remained the same. How could the current remain the same when the diameter is changing so much? And that's because it's all running off of a single silicon filament. All of them are forming the same filament. Whether you have a big device or a small device, there's a single filament. So it's a filamentary metal conduction. So you're forming some silicon. This is a silicon wire buried in silicon oxide. You bring it up to a high enough voltage, that is going to break, and you then just scan it back and it forms. And then it's point switching. So it was independent of the silicon oxide thickness. Whether the silicon oxide was thick or thin, it didn't matter. So all of these things cued it in for him. And then what he did is he wanted to observe the actual switching area in that damaged silicon oxide. So he built a TEM probe. So this is a transmission electron microscope probe where you put your samples on the end. But he designed it and he built it in the clean room here, in the machine shop here. So this was going to cost $90,000 to buy, just this piece. And I said, I can't afford $90,000 just for a single experiment. So he built this for $1,500. And so this is just a TEM probe where you can apply a voltage. You can apply voltage in the TEM probe. So he's going to apply a voltage across a carbon gap and induce a filament, and he's going to make this so thin that you can do the transmission electron microscopy through it. So here's what he actually built. Here's the gold pads that you attach the electrodes to, and then here's your carbon, and then here's the underlying silicon. And so this is all put into this setup that goes into a transmission electron microscope. It goes under vacuum and you record it. And here's what it looks like. If you zoom in, you can see here's the silicon oxide layer, and there's that thin carbon film on top of it. The thickness across this is 100 nanometers thick. The guy's amazing. Just amazing what he could build here. And so he's looking, this is his TEM probe, he's looking right down in here, right where this nano gap is. So here's the carbon, the amorphous carbon, the alpha carbon, the amorphous carbon on the silicon oxide. And he's then going to induce a voltage here, and that voltage is going to cause a breakdown, and you would see this breakdown. So you can see how this has gone to this smooth edge of silicon oxide, and then the thing is just damaged here. And he's trying to see the crystal of a silicon filament going through this. And he was able to observe that. He was able to observe the crystal of silicon going through this. So actually we could publish this paper. It was really amazing what he pulled off here. And so if you look at how this thing evolved, we had these nano cables, we had this carbon film that broke, and then this carbon film that broke, and then Stanley was seeing the same sort of thing, and then there were other people suggesting similar things going on at about the same time. That's what happens in science. Different things start coming in from around the world. Different people start seeing the same phenomenon. And then we built some arrays and we sent them up into the International Space Station. And why would we do that? Because they put these in high radiation areas. We wanted them to undergo a lot of exposure to radiation to see could they withstand space radiation. So it was in the International Space Station in a high radiation environment in space for little over 2 years. The first set we made they were going to go up in an unpersoned vehicle that was taking off out of Russia. And that vehicle blew up going into space. And so there was nobody in the vehicle, but our samples were, So then we had to remake them, and then they went up again. I think they went up in a Soyuz rocket, and they went up into the International Space Station, and they stayed there for a couple of years. And then they came back, and we were able to test them, and there was no memory loss. So we showed that they're resilient in space, because this is important. If you're going to do a mission to Mars, it's going to have to have radiation-hardened electronics. Then I had another person in the group, and she said I tasked her with building a crossbar memory, where you have reading lines. A crossbar is a typical reading type memory, and to also make us some transparent memory, because if this is made out of silicon oxide, you can just use glass and it could potentially be a transparent memory. Now, the memory you have in your phone is not transparent, but if it could be, that would be really neat, so that glass panel on the front, instead of just being a piece of glass with indium tin oxide on it, it could be your memory as well. So it'd give you all your memory. It could be in there if you could make memory transparent. So I had one woman say, you cannot build a crossbar out of this. She went to the lab, she tried, and she said, it's impossible. And she was a Russian woman, very smart, but she was convinced it could not be done. And I hired Javan Lin, and I didn't tell him what she said, and he made it work. And this is what happens. I mean, you just don't tell them that it can't be done, and somehow they get it to work. And Javan is now a professor at University of Missouri. And so he built first this transparent memory, and you can see it right here. It's transparent memory. Here it is on a piece of glass. Just put over the Rice logo, and you see, I mean, this is really quite transparent. And the memory is built into that. And then he put it on flexible plastic, and the memory is built into that. And so you can see the switching states. It's doing the same, about 10 to the minus 11, 10 to the minus 12 off, 10 to the minus 5 on. And you say, well, who wants it in glass? Well, who wouldn't want it in glass? Look how much building material is glass. If you look at buildings these days, there's just so much glass on large buildings. So if you can build functionality into that glass, where you can put memory into that glass and electronics into the glass, then you could, for example, you could have, you instead of shutting shades at night, you just push a button, or you just say, Siri, darken the glass, and boom, now it becomes opaque. You can't see through it. And then, or if the sun is too much in your eyes, you just say, Siri, just darken it gradually, right there, stop. I mean, wouldn't that be nice to have in there? Or your whole touch panel is just all in the glass. It's not a sheet of glass over a bunch of other electronics. It's all in the glass. That's all you have. Then you'd have to build all the things transparent. And so he built these vertical structures like this. Then he built the crossbar memory. Here's the crossbar memory that she said couldn't be built, and he actually built the crossbar memory, and he built it transparent, because he just used graphene sheets as the wires, as the conducting wires. And so now you had the silicon oxide between these, and since the graphene is transparent in the visible region, you could have transparent memory, you could have the on and off state, and now it's in a crossbar memory. a great advance what he did. And then Ganuk Wang came on, and he really pushed this along. He come from a hardcore electrical engineering background, device physics, electrical engineering, and he pushed this and he made this so it had multiple memory states, so you could get like 8 states of memory into this thing, so that each device had like 8 different states, and then he could study the on and off over 100,000 switching cycles. You know, your little flash stick, that's only guaranteed for like 10,000 cycles. That's it. But how many of you write to your flash stick more than 10,000 times? You lose it, right? You lose it before you ever write more than 10,000 times. And so this lasts longer than that. This can switch more than that. So this was really nice findings. And then he tracked it where our material was relative to all other materials that were on the market. What is our sec current? What is the power? What is the forming voltage? What is the on to off ratio? All these different parameters that industry wants to see. Then we started this company in 2016, this Weebit Nano. And I just took this off their website today. So this is what it looks like. And you can go there and you can watch a little video about this. You won't learn anything more than what I just told you, but you'll see a lot of marketing stuff. And so they have these memory chips that they're building that are all ReRAM. See this ReRAM-based memory that's non-volatile. It's 2 terminals. Typically a transistor has 3 terminals. Has the source, it has the drain, and has the gate electrode. This is all based on 2 terminals. When you only have to bring in 2 wires, it's much easier than bringing in 3 wires to every device. Now you don't have gain, but if you have a large on to off ratio, you can still build a considerable crossbar. You build many crossbar memories into this. And it's very good for other types of computing. For neuromorphic computing, it's good for that. So this won't substitute in all applications, but it could substitute for many. And so this is now a public company. The thing about electronics is that you have to have buy-in from everybody that puts something into that. So in other words, if you have a computer that's made by Dell, but that Dell is made up of all different people's devices. So you might have an Intel chip in there. You might have some other Samsung device, some other SanDisk memory device. So lots of different companies have their parts in that computer box. You can't just come in as another company and say, I'm going to put my part in there too. You can't. You have to have every other company that has a part in there to substantiate, okay, your part's not going to mess up our thing. So it's very hard to break in, very hard to get your device into a computing platform, because you have to have buy-in from lots of people, and generally what you have to do is you have to partner with one of the big people, like big people, I mean Samsung, Intel, one of those, Apple, has to go. But the thing about Apple is that they often use other people's parts. All right, I'm talking about the actual base chip makers. And you have to have buy-in from all of them to go into that. All right, so again, here's the people, Yubo Lee. I just can't find his picture. Yubo, if you're going to watch this, you got to, you just search images for Professor Yubo Lee, Hebei University. Nothing comes. This guy is like, the FBI would never find this guy. He's got like no footprint on the internet. And you just can't find him. But here's Alexander, who worked with Yubo and took it on from there. And then Jun Yao, who stood fast and said, this is silicon oxide switching. This is the guy that really made this huge. And then Javan, who showed that you can build crossbars out of it, and you can make it transparent. And then Ganuk Wang, who came from a really hardcore device physics background, engineering background, and showed that, yes, this can be industrially attractive. And when Weebit started, Weebit came out to Rice and spent, I don't know, maybe a month or something. They had device engineers learn from Ganuk of how to do this. And then Ganuk and another postdoc went out to Belgium, where they were building the chips, and helped them do that. And so because you have to get the information transfer. Okay, that's the end. Tell me questions. You got questions? This is the evolution from a basic science discovery to the market. So I just took you through many years. From this was like 2005, 2015, so like an 18-year sequence. That was 18 years. This is a lot of work. It's a lot of work, and you think, well, that's a long time. You know, at Intel, they tell me that from the time something is working reasonably well on their benchtop in the laboratory to the time they're selling it is on average 8 years. So this is a company that dominates all over the place. And from their laboratory to the time they're selling it is 8 years. From the first discovery, I'm talking the first discovery was in about 2004 in our lab. That article in the paper where we showed that this was silicon oxide switching, that was in 2010. So when we knew it was silicon oxide switching, that was 2010. And here we are, 2024. So we're 14 years since the silicon oxide switching. And you add in about another 7 years if you want to say that, you know, from the time we thought it was carbon switching. And interestingly, there was another little thing that happened which is interesting on this. Remember I told you we were funded by SanDisk? So then we went out to SanDisk to tell them that it's actually not this carbon filament switching, it's silicon oxide switching. And I brought Jun Yao with me because Jun Yao really knew the electronics. I'm a chemist. Jun Yao was a applied physics student. And you say, well, students, they don't know as much as the professor. No, graduate students often know more about the topic than the professors themselves because they're the ones in the lab doing this all day, every day, this one subject, and the professor's got all sorts of other areas he's doing, and he's, or she is running into classes and teaching these sorts of things. The graduate students just focus on this. So I brought him with me. I presented the introduction, and then he presented the hardcore, and they didn't like it at all. You'd think they'd be really happy. They hated it. They said, look, we have a silicon oxide switching device. They did, and it was a write once memory, write once, read infinitely. So what happens is they had silicon oxide between two leads, and they would put a high voltage, and it would get breakdown and fuse the two electrodes together. That was now the bit of information, and that's for write once memory. You'd be like, why would you want write once memory? Sometimes you want write once memory because you're recording, say, a book. You don't want that book to change. You want that book to be the same electronic format in 100 years. You don't want memory based on, you know, just a few electrons being able to slip out. You want something that's really going to be there for a long time. So this write once, it's called write once archival memory. It's really going to stay there a long time. So they had this. And they said silicon oxide breaks down. We know it breaks down, but it's not going to give you reversible switching. We said, we're seeing reversible switching. When I got back, they said they didn't want to fund us anymore. And they wrote a letter to the university, even though since they were funding us, they had right to first refusal to all the intellectual property. They absolved themselves of that. They said, we don't want the intellectual property. We're not interested in this. We're not going to fund it anymore. But that was like my lucky day. Because now they didn't own any of the intellectual property. And I could start my own company around this. So it was like, it was the best of everything. They gave up on this. And
you kept all the money that they had given you already.
Well, it was already spent.
Oh, yeah.
It's not a matter of keeping. It was, you spend very fast. So there was no more money left. But anyway, that's kind of the saga. That's what's going on here. So any questions? Yes.
I haven't had much exposure to all this electronic stuff, but I wish I would. Do you think like this kind of stuff, like electronics or technology, should be a core subject for K through 12? Do you think?
Well, I think you always have it in high school physics is when you first start getting electronics, no?
Not for me.
Don't you get some electronics in high school physics?
I do.
Yeah, you get some, and then even a chemistry student has to take physics here. In physics, you get electronics, right? When you take your physics class, you get some electronics, and I didn't really know all of this stuff till we started working in it, and I learned this from my students. You know, I learned this by by working with all these applied physicists and electrical engineers, and that's how I learned it. And I still don't know it well. I just know it enough to parrot my students. Whatever they tell me, I can come up and repeat it. That's about where I am. But so this is what we got, and that's the transition. That's the saga on how you take something from laboratory discovery all the way to market. If you're enjoying this series, give us a thumbs up and click the subscribe button, and that way you'll hear when we're coming out with new videos. There are no salaried employees in this organization. All the accounting, all the legal work, that's all done by friends of mine. The only thing that I have to pay for is the production work, and if you could help us out with that, I'd appreciate it. There's a link below where you can just click on that and help us in several different ways. Thank you.